In this mini lesson, we'll be looking at how to run an ANOVA or other general linear models like ANCOVA and linear regression in SPSS using the point and click features and syntax. So here we have the simulated data set. What we're looking at here is the outcome variable happiness on a 1 to 10 scale. Then we have three different groups. We could imagine group 1 is in a group of people who do not exercise, group 2 is a group of people who do strength training, and group 3 is a group that does cardiovascular exercise. And then finally here in the third column we have age of each participant. So each row in this data set is corresponding to one participant, and you'll see that the first 20 observations are from group 1, the next 20 from group 2, and the final 20 from group 3. So as mentioned, we'll be looking at ANOVA, ANCOVA, and linear regression, and so we can start with the ANOVA. And so you'll notice that there is no option for ANOVA here, it's instead under General Linear Model, which is not to be confused with what's right underneath it, Generalized Linear Model. So the general linear model is actually not as general as it may sound. It's actually a specific case of the generalized linear model, and the ANOVA, ANCOVA, and linear regression, are all types of general linear models. Generalized linear models that are not general linear models include logistic and Poisson regression. Those would be used for outcome variables that are binary or maybe count variables, respectively. We won't go into that in this lesson, but will be a topic for future discussion. So for now, if we just go to general linear model, I get myself confused, we'll be looking at a univariate analysis today because there's just one outcome variable, happiness, that we're interested in. If we had multiple outcomes, we could look at multivariate, or if we had repeated measures where the same participants were measured for their happiness at multiple different time points, we could do repeated measures. But we'll stick with the univariate analysis. So we'll see that I already have loaded in here some of the variables, but I'll just back those out. So our dependent variable is happiness, so we can click that and put it under dependent variable. This fixed factor represents our independent variables. The reason it doesn't say independent variable here is that it splits these up into fixed and random factors. We'll talk more in another lesson about what the difference between those are, but generally what you think of as an independent variable is a fixed factor. And we'll move age down here into our covariate in a future analysis when we do an ANCOVA, that's an analysis of covariance, but for now we'll leave it be. We'll also want to conduct a post hoc test for this ANOVA. What the post hoc test allows us to do is that after we run our ANOVA, it's going to give us an output and tell us whether or not there's a significant difference between our groups in terms of their happiness. But it won't tell us which groups differ from each other. So it might be that all three groups are different. It might be that one group is different from another group, but the same as the third group, and we don't know which way all those relationships might work. So by running a post hoc test, we will get a test of what those differences are. So we'll move our variable group over here into the post hoc test for, and we'll run a least significant difference test. You'll see that there's a bunch of different tests we could run here. All of them are trying to accomplish the same thing, but they do it in different ways. The LSD test is essentially like running a t-test, which if you're watching a video about ANOVA, you're probably already familiar with a t-test. And so this just runs t-tests on each of the group's comparisons. So we can click continue here. And then also go to options here, and you'll see that there's an option for descriptive statistics. So we'll click that box so that we get those in our analysis as well, which will be helpful for reporting our results. So with all that, we can now click OK to run our analysis. And you'll see that SPSS loads this output file. First, we'll just see this descriptive of the sample size for each group, and you'll see that there's 20 in each of these, which is helpful just as a check to make sure that the data are appearing in our output as we think they are in our dataset. You'll notice here that there are these values for the group numbers, but in our dataset, we just have these numbers 1, 2, and 3, so how did these values get here? If we go to variable view, under this group row and the values column, we'll see that there's some text entered there, so we'll click into that. And you'll see that here the values are labeled. So for managing our data, we'll want to use these simple codes like 1, 2, or 3 to code our data, but we also need to know what those codes mean, and so we're able to do that with our value labels here. In in addition to keeping straight which groups correspond to which group numbers correspond to which groups, it also helps us in the analysis as it makes it easier to read, so we don't have to try to be remembering what the group numbers mean. So we'll return to our output file here. We'll see that we have our descriptive statistics. So just by eyeballing this, it kind of looks like the cardio and strength groups are pretty similar to each other, but are a little higher than the happiness for the no exercise group. But we'll want to confirm that statistically with our analysis. So here, this is the test of between subjects effects. This is essentially the stats for our ANOVA. The main test that we're interested in here is this group variable. So this is the independent variable of interest. It shows us some statistics on the overall model, the intercept, and the error as well. But as I mentioned, we're interested in this group variable. We'll see that there are 2 degrees of freedom, which since there are 3 groups, 3 minus 1 is how we calculate the degrees of freedom. So we have 2 degrees of freedom. It gives us the F value. And most interesting to us is this p-value, or in SPSS it just says sig for significance. And this value here is 0.033. So using a standard level of significance of 0.05, this value is less than that, and so we would say that there's a statistically significant difference between the groups. But again, that's all we can say right now because we don't know which groups are different from each other, and that's what we run the post hoc test for. Here in the post hoc test, it's comparing all the different pairings of the groups. So first we'll see that the no exercise group is compared to the cardio and strength groups. We'll see that the mean difference between those is 1.6, so the cardio and strength groups are 1.6 and 1.65, happiness points higher than the no exercise group. It also gives us the confidence interval around that difference. And again, interesting to us is that we are going to use this as our statistical test to decide whether or not there is a significant difference between the groups. And we will see that in both cases, the significance level is less than 0.05. And so we would say that the cardio and the strength groups both have significantly higher happiness levels than the no exercise group. You'll see that some of these kind of repeat as we kind of go down this matrix. Now it looks like cardio and no exercise again, but we already looked at that above. But now there's cardio and strength, which we haven't looked at yet. We'll say the difference there is 0.05. That's just the raw scores. So there's the strength group is 0.05 points higher in happiness than the cardio group on average. And unsurprisingly, with a difference that small and a relatively small sample size, we don't see a statistically significant difference between these two groups. 0.943 is higher than 0.05. So from this, we conclude that there is a significant difference between the groups in terms of happiness levels, and that's driven by the cardio and strength groups each being higher in happiness than the no exercise group. Now, I ran this with the point and click method, but we can also do this running SPSS syntax. Now, one way you can do that is you can go to File, New Syntax, open up the syntax, and then start writing what might be your code for your analysis. And so we might run ANOVA, and then we might enter our variables and so on. But if you're just starting out with SPSS syntax, you probably won't know how to do that. You won't know the syntax to run. So there's a very helpful thing you can do in SPSS, which is that if you just go back to that same analysis you just ran, it'll actually first load up the same analysis you just did so you don't have to re-enter it again. But now, instead of before where we clicked OK, if we click Paste and go back to our syntax file, we'll see that our analysis is already loaded into our syntax file. So it took what we did with point and click and turned that into syntax, which is essentially what we'll be running on the back end, not visible to us when we use point and click, and it now presents that to us in a syntax file. Now you might think that point and click just seems really easy, so why would we use syntax? Well, one thing might be is that you might want to share your results with other people or have them generated themselves. And so you don't want to have to say, click this button, then click this button, then click that button, type that all out. It'd be really nice if you just had one file where you could just have this all together. Also, if you run a whole bunch of analyses and then decide you want to go back and change something about the way you ran one of them, you can now just use this and go back and change in and maybe say, I want my significance level to be, 0.08 and, change that. So it just makes your code more modifiable in the long term so that you don't have to go back going through these analyses click by click. And now if we want to run these analyses, we just highlight that, and we can press this green button here. And what we'll see is we get back the exact same thing that we had up above. So the group test significance level is 0.033. Again, a difference of 1.6 between cardio and no exercise. Cardio and strength are both significantly higher than the no exercise condition. So all that came out just as we had it before. Now, maybe one person might say that, this analysis we did, we just compared the differences between groups, and we're now concluding that there's a difference in happiness between groups. But maybe there's something else that's driving this difference in happiness. Maybe, for example, it's not that people who exercise or don't exercise, that necessarily makes them happier or not. Maybe what it is that people who exercise are typically younger, and maybe younger people are just happier, and that's what drives our results. So what we could then do is we could run an analysis of variance, but have a covariate for age. This is called an ANCOVA, analysis of covariance. So we can go back up to Analyze, go to General Linear Model Univariate again. We have this same analysis loaded in, but now we have this covariates box where we're going to add age into. You'll notice that when we do that, the post hoc box here grays out. The reason is that we can't directly calculate the post hoc test because now we have this other variable in the model, and the model is partitioning variance between these two variables. But what we can do is we can calculate estimated marginal means. So just like we can calculate means of our data without even running a model, the estimated marginal means allows us to run the model and then essentially calculate the mean of the group, accounting for the differences in age. So it's taking out the variation in groups' happiness levels that might be attributed to age, and just getting us what the mean of the group factor is. So if we click the group button, we can go over to display means for that, and we're going to compare the main effects. And so this gives us not just the estimated marginal means, but essentially gives us what's like a post hoc test of what we did before. You'll see again that we can use the LSD, least significant difference. So this is not going to adjust for multiple comparisons, which is something that you might want to do in certain cases. For right now, for simplicity's sake, we won't do that. We'll just keep it with no adjustment here using the LSD test. We can click continue. And now we can run this model. We'll use it doing this syntax, and we'll click paste. We'll go back to our model. We'll see here that what we're seeing that's different from our previous syntax is just this addition of the EM means line that's replacing the post hoc line from before. So the estimated marginal means are looking at the variable group. It's doing that by age, using the covariate of age, adjusting for that, and it's not using it's using the comparison adjustments of LSD, which is essentially not making an adjustment for multiple comparisons. So now if we highlight this and run these analyses, we'll see that again we have 20 people per group. We have our descriptive statistics again. We have our ANOVA. This time you'll see that there's also the variable age in there. From this we can see that the variable age is not significant. It has a very small estimate here, which is going to lead us to believe that it's probably not going to affect our analyses in terms of the group differences, but we can check that below. So now here are the estimated marginal means. And first, let me go back and mention that the group variable here is still statistically significant. So there still is an overall effect of the group. When we go to the estimated marginal means, we'll see that again, the cardio and strength groups are very close to each other, and the no exercise group mean happiness is a little bit lower. And then here, again, this looks a lot like what we saw before with our post hoc test for our ANOVA, and when we come down here for our ANCOVA with the estimated marginal means, it's very similar. So when we're looking at this, we now see that no exercise versus cardio and strength, there's a similar difference, 1.6, 1.65. The cardio and strength groups are higher than the no exercise. And the significance value here, the p-value, is again less than 0.05. So we still conclude that cardio and strength are significantly higher in happiness than exercise, when accounting for variation in age between the groups. If we compare cardio and strength, there's no significant difference there. So again, 0.05 is our significance level, 0.943 is higher than that, so we conclude there's no significant difference between cardio and strength and happiness levels overall.